Hello and welcome to this video on what is classical test theory. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods such as factor analysis models, structural equation models, and latent class analysis. I also sometimes cover issues related to measurement and psychometrics, like in this video. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as courses that I teach for QuantFish. In this video, I want to introduce you to the basics of classical test theory and show you what classical test theory does and what it is good for. So let's dive right into it. What is classical test theory? Classical test theory is a measurement theory that deals with the measurement error problem that we have in the social sciences. When we measure, for example, intelligence using intelligence tests, or personality using personality questionnaires, or something like depression and anxiety in clinical psychology, then typically those tests and questionnaires, they are not perfectly reliable as measurement instruments, and so the scores, the test scores or questionnaire scores, will be contaminated to a certain extent with measurement error. And that is due to random influences, such as, for example, a person getting distracted during a test, a person randomly misunderstanding or misinterpreting a question on a questionnaire, an investigator incorrectly entering the test scores into a database, making some typing mistakes or something like that. So random errors of measurement happen, and they obviously add random noise to our test scores. Now, why is this a problem, first of all? It's a problem because oftentimes we use tests for diagnostic purposes. For example, we want to select individuals sometimes for jobs, or we want to select individuals for college degree programs, for scholarships, for awards, for something, and then we want to make sure that the test scores accurately, precisely reflect what we want to measure, whatever that is. So we want to make sure the test scores are precise and they're not totally off, so to say, where an individual's intelligence would be vastly underestimated or vastly overestimated because there's a lot of contamination by measurement error. Likewise, when we use questionnaires about depression or anxiety in clinical settings, then we would want to make sure that we do not miss a person who has a severe disorder because maybe there's measurement error indicating that the person isn't that anxious or isn't that depressed, when in fact they really are. So there could be an underestimation due to measurement error of anxiety, for example, or an underestimation of the level of depression. And so it's very important for us that our test scores be as precise as possible so that we don't make errors in diagnoses when we diagnose people, when we select people. That's one reason. Another reason is that when we use measurements, when we use variables in statistical analyses, for example, in research projects, when we want to look at, for example, in a research project, does intelligence predict job success? Then also measurement error can lead to problems because measurement error waters down correlations between variables. It, as I already mentioned, it adds random noise to the scores, and the effect of that random noise on correlations is that the correlations will be attenuated, or we could say underestimated, such that the observed score correlations do not adequately reflect the true score correlation. So we would underestimate the strength of association between different constructs in, for example, correlation analysis, in path analysis, in regression analysis, in other types of analyses that use or are based on associations between variables. And so that's one reason too why we need classical test theory. Classical test theory provides corrections for measurement error. later on. So first of all, it tells us what error is, how that's defined, how we can measure it, but then also it provides correction. So for example, on this channel I have a video on the correction for attenuation, where I show how classical test theory can be applied to adjust the correlations between variables for unreliability, and how we can estimate the true score correlations between variables that are not perfectly reliably measured. So in summary, classical test theory addresses an important issue in the social sciences, and that is the problem of measurement error. It allows us to define what measurement error is, also what a true score is, how that can be formally mathematically defined, and it allows us to come up with a definition of reliability. So how can we measure that? How can we express reliability in a single number, in a statistical index or coefficient that allows us to quantify the degree of reliable variance in our measures as opposed to the proportion of unreliable or measurement error variance. And then finally, classical test theory provides us with measurement models that are testable, that we can fit to the observed data to see if, for example, different measures are parallel in terms of what they are measuring. Do they measure the same true score variable? For example, do different tests of intelligence measure the same true score that reflects intelligence? Or are they heterogeneous? Do they measure different factors, different true scores? And then based on these measurement models too, we can estimate the relevant parameters for the true scores and error scores that allow us to compute reliability. So the measurement models are a vehicle to obtain, for example, an estimate of the true score variance and of the error variance for a given test. And then based on those variance components, as we will see, we can define a reliability coefficient. So that's in a nutshell pretty much what classical test theory does. Now let's dive into the details, and I'll show you that in more detail on the following slides, how this actually works. So what are the basic ideas of classical test theory? First of all, in classical test theory, errors of measurement are considered to be random or unsystematic, we could say. And so based on that, we can make a thought experiment such that we could imagine hypothetically that we might test individuals indefinitely, an indefinite number of times, with the same test or measurement. So we would administer, for example, the same IQ test a large number of times to the same individuals, and we would assume that in between we do something like brainwashing. So we wipe out the individual's memory of previous exposure to the test, so they wouldn't remember anything. So they would come in fresh for each trial, for each administration of the same test, they would start over. So that's of course purely hypothetical. We could not do something like that in practice. It is purely a thought experiment to help us understand how a true score is defined in classical test theory and how an error score is defined in classical test theory. So again, this is purely theoretical. It's not a practical thing at this point, but it helps us understand classical test theory. So if we could do that, if we could repeatedly administer the same test over and over and over again to the same people with no memory effects, no fatigue effects, no learning effects, no other effects of prior testing, then we would obtain, due to measurement error, an intra-individual distribution of scores for each person, for each individual, because the test scores would not be the same, despite the fact that we would assume that intelligence is the same or remains the same for a given person. They would still provide us with different scores across these different trials simply due to random errors of measurement. So in one trial, a person is less focused, tired, is distracted. In another trial, they are particularly alert, they're particularly sharp, and so there will be some random fluctuation in the scores simply due to random noise, random measurement error, and so that then results in this intra-individual distribution of scores. And so the idea then is that across these many independent trials, the errors of measurement would average out. So they sum to zero basically, because sometimes the person will be scoring higher than typical, sometimes they will score lower than typical due to error, sometimes there'll be no error and they'll score exactly at their average. And so, but there will be a distribution, and so say if we take the mean of that distribution, then that's our best guess for what that person's true intelligence score is. True here meaning the score that is least contaminated or uncontaminated with measurement error. So let's take a look at that to make it a little bit more concrete. So here I have the hypothetical intra-individual test score distributions plotted for 3 hypothetical individuals, Amy, Max, and John. Let's say Amy, Max, and John took an IQ test, and let's say they took it repeatedly, and there was no memory, no learning, no fatigue, no whatever other effects of prior testing. So we were able to wipe out Amy's and Max's and John's memory after each trial, and they took the test fresh each time. And then, for example, for Amy, we might see a test score distribution like this, where sometimes Amy scored really low, sometimes Amy scored higher, and we have an average here in the middle as indicated by the filled black dot. So we might have observed, for example, in a given trial, that test score up here for Amy. So this would be our observed test score Y. But you can see that this observed test score is quite a bit away from Amy's intra-individual average across this hypothetical set of independent trials. So this would be the true score by definition in classical test theory. The mean of Amy's intra-individual score distribution is defined to be the true score in classical test theory. And so if we were to observe the score up here in our actual testing situation with Amy, then we would be quite a bit off. And so that discrepancy between Amy's observed score Y and Amy's true score tau, her intra-individual average, that is defined to be the error score epsilon in classical test theory. So the difference between the observed test score Y and the true score tau is equal to epsilon. Now, of course, this is hypothetical, it's latent, so to say, or unobserved, because we do not know Amy's true score. We would only know Amy's true score if we could actually carry out this thought experiment, which we cannot. In practice, that's impossible. We're not able to ask Amy to come in 100 times to take the same IQ test, and we cannot wipe out her memory of the test. We cannot exclude her from learning, or we cannot somehow make her not learn the items and get better on the test. We also can't avoid her becoming annoyed and fatigued with the test. So that's not something that we can actually do. But in theory, so to say, if we could do it, then the average of that set of independent trials, the average score, that would be Amy's true score. As we will see later here in my presentation, it's not necessary either to know what Amy's true score is exactly. We can still estimate what is called the true score variance. So the variance of the true scores inter-individually is something that we can actually estimate under certain assumptions that we can make. And that's enough for us. So in order to determine reliability, we do not need to know the individual true scores. All we need to have is an estimate of the true score variance across individuals, but we'll see that later. So far so good. Now this tells us how the true score is defined in classical test theory as the intra-individual average score across these hypothetical large numbers of trials, and we know what the error score is. It's the difference between the observed score and the true score. Now for other individuals, we would get distributions also. For Max, you can see the true score, the average is higher than for Amy, and the variability in the scores for Max is lower, so there's less error variance intra-individually in Max's set of scores. John has a little bit more variability again than Max and a lower true score, but still a higher true score than Amy. Now, this also illustrates that measurement error can be quite problematic in practice, because imagine that we really did observe Amy's score that is indicated up here, and we did observe a score for Max that is down here. So let's say this was the score that we actually observed for Max. Then we might say, based on the observed test scores, that Amy is more intelligent than Max. However, that's actually not the case. When we look at the true scores, when we look at the intra-individual averages, you can clearly see that Amy's score is lower than Max's score. And so this discrepancy here would be totally misleading, or this difference between these observed scores would be totally misleading for the actual true score difference. And therefore it's important to measure the amount of error, or to find out how much error there is in the scores and to correct for it if necessary, or to develop more reliable measurements if it turns out that the measurement error variance is too high. So this shows you that measurement error problem is really an issue, because we have these hypothetical intra-individual score distributions, and we might end up anywhere here when we actually carry out the testing. Then we might observe any of these scores, and then when we have comparisons, we want to make comparisons between people, then those might be misleading because of measurement error. In summary, classical test theory decomposes a test score variable yi, so I here stands for a specific test, for example a specific IQ test, into a true score variable plus an error variable, and it does that for every individual test. So let's say we have an IQ test 1, then that IQ test 1 has its own true score variable tau 1 and its own error variable epsilon 1. Another test 2 would also have its own true score variable tau 2 and its own error variable epsilon 2. And then again, a third test would also have its own true score and error variable in the basic decomposition of classical test theory. Later we will see that when we formulate actual measurement models of classical test theory, we make homogeneity assumptions about those different true score variables if we hypothesize that different tests may measure the same true score or perfectly correlated true score variables. Then we might say, for example, that test 1, 2, and 3 are parallel such that they share the same true score variable, and then we have a measurement model of parallel test score variables. But for now, so to say, in the basic decomposition, each test score variable has its own true score and its own error variable in CTT. There are some key properties of the true score and error variables that follow directly from their definition. Remember, the true score is defined as the intra-individual average of that hypothetical score distribution within each individual, and the error score was defined as the difference between an observed score and the true score for a given person. And so there are some properties that follow directly from these definitions that are important. The first property is that the mean or expected value of the error variable epsilon I for test I is always 0. So there's never a mean that would be estimated for an error variable epsilon, because errors of measurement sum to 0 within each person by definition. So there are by definition positive and negative deviations from the mean, and they sum to 0. That's, so say, the definition or property of the mean. And so epsilon, then the epsilon scores within each person for each intra-individual score distribution sum to 0, and that has as a consequence that epsilon also has a mean of 0 as a variable. So we never have to estimate a mean for an epsilon variable. That is 0 by definition. Furthermore, epsilon is uncorrelated with true score variables. So the covariance cov between epsilon I and tau j is 0, means that error variables do not correlate with true score variables that either pertain to the same test or different tests. And so that's another important property, because that leads to an additive variance decomposition, which is key in classical test theory for defining reliability, as we will see. So because of the independence, the linear independence of epsilon and tau, we can additively break down the variance of an observed test score variable var yi into a true score variance, variance tau, plus error variance, variance epsilon. Those are independent variance components, so to say. And that then allows us to define a key measure in classical test theory, which is the reliability coefficient. The reliability coefficient is defined as a variance ratio, variance in the true scores divided by variance in the observed scores for a given test I, where the variance in the observed scores, as we saw on the previous slide, is equal to the sum variance tau plus variance epsilon. And so now you can see that we don't actually have to estimate individual true scores. So we don't need to know what true score Amy has or what true score Max and John have. All we need are the variances, so to say. So between person differences in the true scores and between person differences in error scores. And so that's reflected by these variance parameters that can be estimated. Even if we do not know the actual true scores for the people in our sample or population, we can still estimate those variance components. And that's part of the magic of test theory, is that that's possible. Even though you will never know what is Amy's true score, what is John's true score, what is Max's true score. We don't know that, but we can still estimate those variance components. And that's all we need to calculate a reliability coefficient for a given sample. So let's take a look at that also, how this works. And I'll give you one example where it's pretty simple, and then there are other examples that are less simple that I discuss in my course, my QuantFish course on classical test theory, that you find in the description. So let's take a look at a simple example. First of all, one thing that I forgot to mention is that reliability of 0 indicates that the test scores are completely unreliable, meaning there would be no part of the variance in the observed scores would be true score variance, all of it would be error variance, whereas a reliability coefficient of 1 would indicate that the test scores are perfectly reliable, meaning there's no error. All of the variability that we observe is true score variance. In practice, reliability coefficients that are typically, or for scales that are typically used, range between, let's say, 0.7 and 0.95. Intelligence tests tend to be highly reliable, so they have often reliability coefficients above 0.9. Questionnaire scales, especially when they're shorter, when they have few items, they may be more in the range of 0.7 or 0.75, but there are also questionnaire scales that are highly reliable. So typically, we would say that we would want to have a reliability, let's say, above 0.8, 0.9 ideally, where only 20% of the variance in the scores is error variance, or 10% of the variance in the scores is error variance. So the reliability coefficient gives us the proportion of variance in the measured scores that is true score variance. Now let's take a look at how we can actually estimate those variance components that go into the formula here for the reliability coefficient, and that is one thing that we need measurement models for. It doesn't work without classical test theory measurement models. And I will show you one measurement model that is the simplest, most restrictive measurement model of classical test theory, the tau parallel model, or sometimes we say the strictly parallel model. In that model, we make assumptions about the homogeneity of true score variables. And those are restrictive assumptions that are testable in practice, that can be falsified, so to say, that define measurement models that can be tested against the observed data, and where we could reject the model if the model doesn't fit our data. So what does the tau parallel model of classical test theory assume? First of all, and that's the restrictive assumption here, is that the true score variables for different tests are equal. So let's say we have two tests, 1 and 2, then the true score variable tau1 is equal to the true score variable tau2, so that we can drop the index or subscript and there's only a common true score variable tau. And if we had more tests, then that would hold true for all those. So tau I equals tau j equals tau for all I and j, we could say in general. So the tau parallel model assumes the identity or equality of all true score variables. So for example, if you had multiple IQ tests, then the tau parallel model would say they all measure exactly the same true score variable. And then as a consequence, we can replace those individual true score variables by a single common true score variable or factor. Furthermore, the model assumes that the error variances are equal for all tests. So in the case of 2 tests, we would have variance epsilon 1 is equal to variance epsilon 2 is equal to variance epsilon. So there's only one error variance parameter to estimate. That's to say, that means they have the same reliability, those different tests, under the strictly parallel model. And then furthermore, we assume that different error variables for different tests are uncorrelated with one another. Then the resulting model looks like this. It's a confirmatory factor analysis model with a single factor and equal factor loadings and equal error variances for epsilon 1 and epsilon 2. So this model then has only 3 parameters. It estimates only the true score variance, variance tau. It estimates the common error variance, variance epsilon, and it also estimates a mean for the true score variable. So it has 3 parameters, and so it's already testable against the observed data, even if you have only 2 variables, because with 2 test score variables, y1 and y2, you have 2 means, 2 variances, and a covariance as observed information. So you have 5 pieces of information, but you only estimate 3 parameters in this model of strictly parallel variables, only true score variance, true score mean, and the error variance that is common to both tests. And so you have a model with 2 degrees of freedom that can be tested against the observed data in confirmatory factor analysis using a chi-square test of model fit. So you could fit this model, for example, in Mplus or in Lavaan or AMIS or any program for structural equation modeling and factor analysis. And so you could test it and you could estimate those parameters. And then based on those estimated parameters, you can calculate reliability. So in this model, the reliability is implied to be equal for all tests because the error variance component is the same. And so therefore we can just simply divide the variance of tau by the observed variance, and that's equal to the covariance between y1 and y2 under the model divided by the variance of y. And so we estimate the variance of tau in the model. We also estimate the error variance, and then in the denominator we could get the observed variance y as the sum of true score variance plus error variance. And so if this model holds true, you could even calculate the reliability of each test based on the correlation between the 2 tests. So 2 strictly parallel tests, their correlation is an estimate of reliability. So it's a very simplistic model of classical test theory. It can be tested against the observed data even with just 2 measurements. Even when you have just 2 tests, you can fit this model, and SPSS even will do that for you and give you a chi-square test of model fit, or Mplus will do it, or any program for structural equation modeling. It'll give you these variance components as parameters, and it'll give you a reliability coefficient to indicate how reliable the test scores are. So this is, so say in summary, what classical test theory does. It defines what true score and errors are. It allows us to define a reliability coefficient, and it allows us to come up with measurement models that can be used to estimate the parameters, the variance components, and that also allow us to estimate a reliability coefficient that then tells us how much measurement error there is in the observed test scores. And that is useful information so that we know about the precision of our measurements. I hope you found this video useful to learn more about classical test theory. Please also check out my other videos on classical test theory on this channel, including ones where I show how measurement models can be fit in Mplus and tested and how the parameters can be obtained in those models. Also check out the description for a course that I offer on classical test theory for QuantFish, and I'll see you next time.